Understanding grounding. If you talk to an electrical engineer, you'll find that oftentimes they'll use the word ground to refer to things such as a reference point from which they're going to measure voltage, or they could be talking about a return path for an electrical current. But in our conversation today, I'm going to talk about grounding as a direct physical connection to the earth. It's important because especially with lightning, if lightning energy enters a system, it can cause serious damage to the equipment, but there's also a potential there for personal injury. The important takeaway from our presentation today is that if you don't properly ground your WeatherTRAK system, you do void the warranty. Grounding isn't that hard to do, and it's not that hard to understand, so we'll talk about the principles today that you need to understand so that not only are you protecting yourself, but you're ultimately protecting your investment in your WeatherTRAK system for many years to come. As we talk about grounds today, we'll talk about a couple of different types of ground connections. A system ground is just simply a system's connection to the earth, which usually terminates in some kind of a grounding point, which we'll talk about in just a minute. The equipment ground is the connection that a piece of equipment or part of the system has to the system ground. When we talk about grounding, one of the most important factors that we'll talk about is ground resistance. Ground resistance is simply a tool that we use to measure how good a job we've done in creating a good connection to the earth. The goal is to achieve as low of resistance as we can. The National Electrical Code requires less than 25 ohms, earth to ground. In the irrigation industry, the ASIC grounding guidelines actually recommends that you achieve less than 10 ohms. In order to achieve that connection to the earth, we actually have to have something that's in direct contact with the earth, and we achieve that with a grounding conductor. On your irrigation system, you'll have either a single ground point or a grid or a group of conductors that are connected together to create a grounding grid or grounding point. These conductors are buried in the soil with good intimate contact with the earth with the exclusive purpose of providing a good physical connection to the earth. There are several factors that we need to consider in order to achieve low earth to ground resistance, and we'll talk about each of them. These include the type of electrode that we use, how well it's installed, and how much of that electrode is in contact with the soil. We'll talk a little bit about soil resistivity and why you need to at least understand that it's a thing, and then we'll talk about bonding. There's a lot of information on this slide that I'm not going to spend a whole lot of time talking about, but it's important to understand that ultimately the most important point is the more surface area that we have in direct contact with the soil, the better. As I mentioned, the goal is to get as much of that electrode in direct contact with the soil as possible. When you're installing the grounding electrode, whether it's a rod or a plate, this is just a couple things to keep in mind. One thing to keep in mind is that when installing a ground rod, in particular in very hard ground, the ground rod may mushroom at the bottom, which creates a little bit of an air gap, which is not direct contact with the soil. It will eventually settle in and be okay, but keep in mind if you're going to be testing the system right away that it might be something that's causing higher resistance than you want. Another thing to be aware of is rocky soils are particularly problematic. I use the example of taking a broom handle and sticking it in a barrel of tennis balls. As you can imagine, there are just points of the tennis balls in the barrel that are actually physically touching the broom handle. The same basic problem exists in rocky soils and is something to consider when installing your ground rod. Another thing to be aware of is when you disturb the soil, in particular with a grounding plate, there is obviously more air space in that soil that's been disturbed. So you should allow that soil to settle a little bit before actually testing the ground resistance. The next important concept to understand is that ground rods and plates, when installed, have a sphere of influence. The sphere of influence is simply the amount of area of the earth in which that lightning energy is going to go. The earth can take an infinite amount of energy without any damage, and that energy is going to go into the sphere of influence area of the grounding electrode that you've chosen. So if we consider a ground rod, for example, if I have an 8-foot ground rod, it's going to be equal to the length of the rod in every direction. So 8 feet below it, or a total of 2 times the length of the rod for the depth of the sphere of influence, and 8 feet in either direction of that ground rod. As I mentioned, the amount of surface area that's in contact with the soil is one of the key points. So if I have 2 electrodes, I have double the amount of surface area in contact with the soil. And 2 electrodes will always be better than 1. It's important that you don't install the ground rods so that the spheres of influence are overlapped. This also means that you want to be aware of your wire path and make sure that you install the ground rods or plates so that those wire paths are not going through the sphere of influence of that grounding point. Because lightning energy, if it exits the system into the sphere of influence from a grounding point and encounters that wire path, it has the potential to jump back onto the system. Here's an example of two 3-point ground grids. The one on the left obviously is installed in a way where much of the sphere of influence from each of the three ground rods are overlapping, and the example on the right is what we want to achieve. For a grounding plate, the sphere of influence follows a similar principle. For example, if I have a 4-foot by 4-inch grounding plate, then my sphere of influence is going to be equal to 4 feet, or the length of the ground plate, in the horizontal direction, and 4 inches in the vertical direction. The other thing to keep in mind when installing a ground plate is that it needs to be at least 30 inches deep and below the frost line. The weakest link in a grounding system is almost always going to be the bonding or the connection of the different points to each other. Connections matter a whole lot. If you're familiar with 2-wire, this is going to sound very familiar. There are different types of connection devices that you can use. One is a clamp, another would be a split bolt connector, and finally would be one called an exothermic weld, or you've probably heard of a CAD weld, which is an exothermic weld. Now, each of these connections can actually potentially fail over time. For example, vibration, corrosion, or mechanical failure can actually decrease the effectiveness of the bond, so you want to take the time to make a really good connection. I personally think that exothermic welds are the best way to go because they're the least likely to fail over time. And I strongly recommend that your grounding bonds or connections be checked on an annual basis just to make sure that you still have a good bond. Here's an example of a grounding point that I tested at a park. The ground rod was installed very well. We measured the earth to ground resistance of this ground rod of about 7 ohms, which is well below 25 and below the 10 that the ASIC recommends. However, you'll notice that there's no connector connecting the copper wire to the ground rod. Essentially, this grounding point was useless for this irrigation system because it didn't have a good bond. Take the time to make good connections on all of your grounding points. The next important factor to understand is soil resistivity. Soil resistivity is simply a measurement of how resistive or conversely conductive the soil is on your site. It's totally outside of your control, but will have probably the biggest effect on your ability to achieve low earth to ground resistance. But I want to make the point that if you have poorly conductive soils or soil with high resistivity, you can consider amending the soil around your ground point with a product such as PowerSet. Now let's talk about what this means for your WeatherTRAK controller. The grounding specification for a WeatherTRAK controller is that for a conventional wire system, that the enclosure of the controller be connected to a good ground. This can be either a system ground or it could be connected to a ground rod that you install near the controller. In the end, what you want to achieve is a good grounding connection that has less than 25 ohms earth to ground. There are just a couple of other things to consider when grounding a 2-wire WeatherTRAK controller. The first is that you need to use a device called the line surge protector. That's going to be installed along your 2-wire path in several locations. The first is you're going to put one at the beginning and at the end of your 2-wire path. So within 25 feet of the enclosure and then at the end of each 2-wire leg. You're going to install one of these devices for every 5 decoders or every 500 feet of total wire length, whichever comes first. If you're in an area that's very prone to lightning, I actually recommend that you install one of these devices every 300 feet. This line surge protector is connected to the 2-wire path and to your ground point, whether it's a single point or a grounding grid. Be sure to install your grounding rod or plate, whichever you choose, so that the wire path is not inside the sphere of influence. And then ultimately, again, we want to make sure that we achieve a good grounding point that's less than 25 ohms. I won't spend any time today talking about how to actually install a line surge protector, but you can check out our website for more information on how to do this. Back to achieving effective earth to ground resistance. As I mentioned before, the goal is to have low resistance to ground. And ultimately, all of the factors that we've talked about, whether it's the type of electrode that we've chosen, or the bonding or the soil resistivity or how rocky our soils all have an effect on how effective our grounding point can be. The only way to really know how effective our grounding actually is that it has to be measured. And really there's only two ways to measure earth to ground resistance. The first is what I call the 62% method. This is actually a derivative of a fall of potential test, which I'm not going to talk about today, but is also referred to as a 3-point test. The other is a clamp-on test. Both of these tests require a specific device and specific method in order to do the test properly. Before I go into testing, I want to make just one point. If you read the ASIC grounding guidelines, they actually make recommendations that the grounding points be measured a lot. As you can see here, the ASIC not only recommends that the grounding be tested after installation, but then every 3 months for a year so that you can determine when the most critical times of the year are, and then they recommend that you test it every 6 months during those critical times to make sure that you are maintaining good contact with the soil. Whether or not you choose to do this is obviously up to you. It's not part of the WeatherTRAK spec. However, it is a very good practice to consider implementing into your standard maintenance routine. Now I want to talk about how to test the effectiveness of your ground point using first the 62% method, using a 3-point ground resistance tester. The first thing that you need to do is to make sure that you disconnect your ground rod from the service ground. That simply can be done by disconnecting your 6-gauge copper wire from the ground rod. The next thing you're going to do is you're going to connect the first point, we'll call point X, of your ground resistance tester directly to the ground rod. The next step is to put a probe in the ground for point Z. The distance of point Z is calculated by taking the depth of the ground rod, in this case 8 feet, and multiplying it by 10. So for our example, our point Z is 80 feet away from the ground rod. If I'm using a ground plate, I want to use 10 times the diagonal distance of the ground plate. What that means is that I measure from one corner diagonally across the ground plate to the other, and then multiply that by 10 for point Z. The next step is where the 62% method gets its name. We're going to measure 3 different times for point Y. The first one we're going to measure at 72% of my 80 feet, or 58 feet, and I'm going to take a reading. Next, I'm going to take another reading at 62% of point Z, or in this case 50 feet, and then again at 52% of point Z, or in this case 42 feet. If all of my values are within just a few ohms, basically less than 3% of a change, then my effective earth to ground resistance is going to be the average of those 3 readings. So I'm going to take my measurement at 52%, at 62%, and at 72%, add them together, and to divide those by 3, and that will be my effective earth to ground resistance. If I'm less than 25 ohms, or if we're following the ASIC guidelines, less than 10 ohms, I have good earth to ground resistance for this ground point. The next test is a clamp-on test. This test can only be done using a clamp-on ground resistance tester. There are several available on the market, and the key point to remember when doing this test is that you have to have a connection to the utility neutral because of how it works, and I'll show you an example here in just a minute. This test is actually really quick and very easy to do and takes only a couple of seconds, but the equipment is generally a little bit more expensive than a 3-point ground tester. It's also important to note that for some 2-wire systems you cannot use a clamp-on test to test the ground. Here's how a clamp-on test works. When you clamp around the conductor of your ground point, it's going to induct voltage, which travels up through the system, finds an upstream grounding point, and allows that current to travel through the ground back to the tester. Because I know how much voltage I've inducted and I measured the current, I can then calculate using Ohm's law what my earth to ground resistance is. Thank you for joining me today as we discuss the basic principles of grounding. It's my hope that with this additional information, you'll make the investment in your WeatherTRAK controller and make sure that you have a good grounding connection. Be mindful of the sphere of influence of your grounding points and where you place them and how you install them. Be sure to make good bonding connections for the entire grounding system. Finally, measure so you know the grounding points that you've installed are in fact protecting your WeatherTRAK system. Thanks again for joining me.